So I want to talk about an interesting structure, which is going to be a second order structure that's going to be of just current sources, basically voltage control current sources, and resistors and capacitors. I'm going to look at the structure and we can talk about putting in some values and looking at it, but just what do I do if I'm faced with this kind of a structure? Well, it turns out that this is actually not that complicated to write the equations down. Initially, I've also noticed everything here is scaled by G. There's a G2 here. Okay, let's take a look at what that means. Well, this is, and by the way, I could have written this as a normalized form of G, and that may have also been a kind of an interesting way to solve it. You could imagine here saying, well, this would be KCL of V1 and KCL of V out. Those two equations give me this core and this core equations. After I'm done with that, in the end, I get two resulting taus, tau 1 and tau 2. And that come out of it, one just coming out of the G and SC, which is basically this G, it's G and SC there, and then the other one here is it's going to be C over G2, which is going to be on this side, which is coming out of the output node structure. Again, notice I've kept both of these equations. Once I've normalized them, everything's in the numerator, so it becomes pretty easy to solve this. I plug V1 directly into here, and I get I get a 1 plus 1s plus tau times an s tau 1 in there, bring the V out to the other side, rearrange the terms. What I end up getting is underneath is a 1 plus an s tau 1 over an s squared tau 1 plus tau 2. And you think, all right, we're in pretty good shape. Tau squared, so the tau is going to be the geometric mean of those two, which is kind of an interesting kind of structure you might imagine there. Of course, if I'm solving for Q, tau 1 is going to be tau over Q. Well, that gives me that Q is tau, is then going to effectively be the tau over the tau 1, which then gives, well, this is in the square root of these two, so it gives me a square root of tau 2 over tau 1. And you think, interesting. I get sort of two time constants, which is effectively this sort of G and this sort of normalized form of G, which I could have normalized them. I could have done a number of different ways to show this. But what's really interesting is that I get sort of the ratio, the square root of the ratio. So things don't move very much, but you could imagine, for example, say the capacitance is 1 picofarad, the conductance, is 1 over 4 meg, and G2 is 1 over 1 meg. What I end up finding for the time constants is 4 microseconds and 1 microsecond. And so as a result, if I did along these lines, what I'm going to find is that my Q is going to end up being a half, and my tau is going to be 2 microseconds in this case. This is one form of a tau-Thomas structure. It's actually what's typically thought of as a form that has when I have a transconductance, which is basically a real form of a voltage control current source and capacitors. In that view, sometimes you call this a diff2 structure, but otherwise everything else follows just as you would expect. So what's really nice is you can take a very simple structure like this and get a very nice complex set of dynamics throughout.